Dear students, in this video we are going to look at the nearly free electron model for describing the properties of metals. In the previous lectures we have discussed about the free electron gas model, and we have seen that the theory of free electron gas is successful in explaining the heat capacity, thermal conductivity, electrical conductivity, etc. But there are some limitations to this model, in the sense you cannot distinguish between metals, semi-metals, semiconductors and insulators using the free electron gas model. And also you cannot explain the positive value Hall coefficient, which is positive for the conduction of majority carriers as holes, and also you cannot explain successfully the transport properties of the metals. Okay. Now, in the nearly free electron gas model, we assume that the electrons in the metals or the conduction electrons in the metals are not completely free, but they are affected by the potential provided by the ion cores. And there is a periodic arrangement of ion cores in the metals, and this provides a periodic potential. And as the electrons travels inside the metal, the electrons can interact with the potential of the positive ion core. Okay. Basically, we will take into account the interaction between electron and the periodic potential in the metal provided by the ion cores. Then in this model, or this model is called the nearly free electron model, and in this model the electrons are arranged in bands, energy bands. These bands are separated by regions in energy for which there is no wave-like solution exist. Okay. And these are called energy gaps. Okay. Now according to this model, you can see there is a plot between energy of electrons in various kind of materials, basically insulator, metal, semi-metal and semiconductors, etc. And a material is called an insulator if the energy bands are completely filled or it is completely empty. Okay. The first two bands are completely filled and the third one is completely empty. And it is called a metal if the energy bands, if there are some energy band which is almost filled, like 90% of them is filled, and there are empty bands in the material. Okay. Those kind of materials are called metals. And in semi-metals and semiconductors, you can see there are some energy bands which is partially filled. These are partially filled, and it is almost filled kind of energy bands. Okay. Band will be having almost filled and another band is nearly empty. Okay. Nearly, so this band is nearly empty. Okay. And this band is almost filled, and this is nearly empty, but there are some electrons at the bottom. Okay. And this is the case with even with the semiconductors. Okay. This band is nearly almost filled and this band is nearly empty. Okay. This kind of materials falls in the semi-metal and semiconductor properties. Okay. So the band structure of electrons could be explained, and in terms of the band structure we can categorize the material into insulator, metal, semi-metal and semiconductors. Okay. Now we just recap the free electron gas model, and you can see we have discussed that a free electron, for a single free electron with wave number k, which is having components x, y, z. Okay. And the energy is given by this expression h cross square k square by 2m. Okay. Now kx, ky, kz for a periodic boundary conditions over a cuboid length L, it can have value 0, plus or minus 2 pi by L, plus or minus 4 pi by L. Okay. This kx, ky, kz can take these kinds of values, and the wave function of the electrons you can write down as a plane wave. Okay. So this is the plane wave in 3 dimension, e raised to I k dot r, and this plane waves carries a momentum p equal to h cross k. Okay. And you can define what is called a Fermi surface. Okay. It is having radius kf, and you know how to find out the Fermi energy. Okay. So these are all about the free electron gas model. And when it comes to the nearly free electron model, what we have is a bunch of free electrons, but these free electrons are not completely free, but they are interacting with the periodic potential provided by the positive ion cores. Okay. And you know, there is regarding the wave propagation, an important characteristic of wave propagation is the Bragg's reflection. Okay. And this Bragg reflection causes energy gap in the metal according to nearly free electron model. Okay. And you know, when Bragg's reflection occurs, there are no wavelength solution, there will be only standing wave pattern. Okay. There is no propagating wave solutions for the Schrodinger equation. To elaborate on this point, let us consider a linear solid of lattice constant A. Okay. Linear, or you can take a simple cubic structure. Okay. With a lattice constant A. Now, you take down note down this picture on the left hand side. So, this gives you the energy of a single free electron, which is parabolically varying with respect to k. Okay. And in the case of nearly free electrons, the plot is slightly perturbed. Actually, the electron undergoes slight perturbation due to the positive ion core. Okay. And the energy gets modified. Okay. For lower part of the energies, okay, so this is the energy axis, and you take up to this part, it is perfectly parabolic. Okay. But as you increase the energy, and this is slightly perturbed. Okay. This parabola is now slightly perturbed, and these are the values. A is a point at pi by a and minus pi by a. Okay. So these are nothing but the first Brillouins on boundaries in one dimension. Okay. So these are the points where the first Brillouins on boundary occurs. Okay. And you can see that there is an energy gap at the first Brillouins on boundary, and this is not surprising in the sense that we have discussed this effect previously, because you know, at the Brillouins on boundary, the Bragg's condition satisfied, and there will be standing wave pattern at the Brillouin zone boundary. Okay. So the Brillouin zone occurs at the first Brillouin zone reflection occurs at a plus or minus pi by a. Okay. And you know what is a Bragg's condition in one dimension, that is in terms of the reciprocal space, the Bragg's condition becomes k plus g square. G square is the a vector in the reciprocal space. Okay. Just like a translation vector in the real space. Okay. And so if you simplify this, you will get k equal to plus or minus half g, and you know, this is equal to plus or minus k can take values n pi by a. These are the points in the reciprocal space. So if you simplify these two equations, you multiply with 2 here, and you get a g equal to 2n pi by a. So this is the reciprocal lattice vector. Now, you know, the first Brillouin zone occurs at plus or minus pi by a, and the wave function at the first Brillouin zone boundary, if you take the one dimensional plane wave solution e raised to I k x, and you can substitute k equal to pi by a plus or minus pi by a, then you will get two wave functions. One is this, and another e raised to minus pi x by a. So these are not traveling waves. These are this will create this is a wave which is propagating in you can take which propagating in a positive direction, and this propagates in a negative direction. Okay. And you know, if there is a wave which is traveling in the right, and another wave which is traveling in the left, they can superimpose. Okay. And produce a standing wave pattern in this manner. Okay. And so since there are two solutions, you can construct two standing wave pattern. Okay, because you can write down e raised to plus or minus I pi x by a according to Euler's formula as cos pi x by a plus or minus I sin pi x by a. So that the standing wave patterns, you can construct two standing wave pattern. One is e raised to I pi x by a plus e raised to minus I pi x by a, that give you 2 cos pi x by a. So this is an even function. So even functions are represented by psi plus. Even function in the sense, as x goes to minus x, this function will give you minus plus psi plus. Okay, so if so it is having a reflection symmetry. Okay, even if you reflect, the wave function remains the same. So such functions are called a even function. Okay, and you can construct another combination. You take the minus sign of these two solutions. Okay, then you will get 2i sin pi x by a, and this is an odd function in the sense, if you take x going to minus x, psi minus will goes to minus psi minus. Okay, there is a change of sign when it undergoes a reflection. Okay, such functions are called the odd functions. Now what is the origin of energy gap? You can explain in terms of the two standing wave patterns. Okay, so this two standing wave patterns behaves differently. Okay, for example, psi plus, if you take the psi plus, this psi plus pile up the electrons at different regions than psi minus. Okay, so the two waves will be having different values of potential energy in the field of positive ion cores. Okay, so in the presence of positive ion core, these two wave functions will be having different energies. Okay, because this will accumulate the electron in some region, and psi minus will accumulate the electrons in some other regions. Okay, and these different kind of accumulated electrons will interact with the periodic potential in a different, slightly different manner. So this will create some energy gap between these two wave functions. Okay, so this is basically the origin of energy gap in a in metals, or in a semi metal. Okay, so this can be understood in terms of the energy density, probability density of the particle. So if you want to find out the probability density, you take this psi star psi. Okay, so this is the probability density, means it is the probability of finding the particle somewhere in the space. Okay, and for a plane wave, if you take e raised to I k x, the probability density will be 1. Okay, so you can take the psi star psi and it will be 1. Okay, but in the case of psi plus and psi minus, and those wave function we know actually, psi plus is basically cos pi x by a, and if you take the probability density of psi plus, then it is proportional to cos square pi x by a, and you know this is maximum at x equal to 0 and x equal to a, x equal to 2a, etc., integer multiples of a. And psi minus is maximum. Psi minus is, you can find out psi minus, is rho minus, which is proportional to sin square pi x by a. Okay, and this is maximum at a by 2, 3, this is 2 basically, and 5a by 2, etc. Okay, so these two objects indicates the probability distribution of the electrons in the space. Okay, so you can see this plot. This plot actually tells you how the ion cores are distributed. The black dots are ion cores, and you know, at the position of the ion core there will be large potential, and as you move away from the ion core, the potential decreases actually. Okay, and for the it is down negative potential. Okay, so we have seen that rho plus pile ups the electrons at 0, A and 2A, etc. That means 0 is this position, A is this position, and 2A, this is 2A position, and this will be minus A position, minus 2A position, etc. Okay. So, accordingly you can see that the distribution, probability distribution of psi plus as at 0 the probability distribution is maximum, and as you move away the probability distribution decreases. Okay. And again at this point at A the probability distribution is maximum and it decreases. Okay. So, all the points which is separated by a distance A from the, or integer multiples of A from the origin, is having maximum probability distribution for psi plus. Okay. Electrons are accumulated at this point. Now, what about the rho minus? Okay. Rho minus is accumulate the electron at A by 2. Okay. So, this is shown by the dotted lines. So, there will be maximum probability distribution. Okay. Now, the if you calculate the average potential energy of rho plus, okay, in the state rho plus, you calculate the average potential expectation value of potential energy in the state rho plus, and which will be less than the potential energy of a travelling wave. Okay. And if you calculate the potential energy of average potential energy in the state rho minus, it will be greater than the potential energy of travelling wave, and this will create a energy gap between these two states. Okay. So, this is basically the origin of energy gaps, okay, between the bands. Now, what is this magnitude of energy gap? Okay. So, you take a Brillouin boundary that is k equal to pi by a, and at this point the wave function can be written as square root of cos pi x by a, okay, and square root of sin pi x by a. These wave functions are normalized over a unit length of the line. Okay. You take a one dimensional line, okay, and whose length is 0 to L, okay, and you normalize the wave function in this one dimensional line. Okay. Then you will get these two wave functions. Okay. Now, let us suppose that the potential energy of electron in the crystal at the point x is the potential. Let assume the potential energy is given by this function, okay, u into cos pi 2 pi x by a, and we have seen this expression before when we have discussed about the Brillouin and the properties in the Fourier space. Okay. And you know, so this is in the reciprocal space actually. Okay. You can see points which is having of dimension of the order of 1 by a. Okay. Now, the first order energy difference between two standing wave states, that means you calculate the expectation value of u of x in the state psi plus and psi minus, then you can substitute all these functions u of x here, and you know what is psi plus and psi minus, substitute, and this is an easy integral to calculate, and if you calculate that you will get the energy difference as u, where u is the Fourier coefficient, because I have already mentioned this is in the reciprocal space and this is in the real space. Okay. And this transformation is basically the Fourier transform, and these components u is called the Fourier component of the crystal potential. Okay. So, the energy difference is given by the Fourier component of the crystal potential. Now, there is a famous theorem for the eigen functions of the periodic potential lattice. Okay. So, it is called the Bloch theorem. Okay. So, the Bloch theorem states that eigen functions of the wave equation for the periodic potential, or the solutions of the Schrodinger equation for a periodic potential are the product of plane wave, okay, e raised to I k dot r times the function u k of r. This is some special function which is periodic in the crystal lattice, okay, which is periodic in crystal lattice. Okay. Solution of the Schrodinger equation for a periodic potential must be of the form uk of r into e raised to ik dot r. So, this is a plane wave solution, and there is a quantity which varies in space, but this variation is periodic. Okay. That means uk of r can be written as uk of r plus t, where t is the fundamental translation vector in the real space. Okay. And so, this is basically called the Bloch theorem. Okay. So, this is this was an important milestone in the condensed matter physics, and you can call the one electron wave function of the form 7 as the Bloch function. You can call this as the Bloch function, and the Bloch function can superimpose to form wave packets which represents the motion of free electron through the positive through the potential provided by the positive ion cores. Okay. Now, how do you prove the Bloch theorem? So, let us take so this first of all I want to mention this very minimal calculation which proves the Bloch theorem. Okay. So, the argument goes like this: let us take psi k to be non-degenerate. I mean there are no wave function with the no other wave function is having the same energy as that of psi of k. Okay. Now, we consider n identical lattice point on a ring. Okay. You consider a periodic potential. So, in one dimensional the periodic potential can be defined using a ring kind of structure. Okay. So, these are all lattice points. Okay. And you starts from 1 at this point is n. Okay. N plus 1 will give you the first lattice itself. Okay. So, according to the symmetry you can write down psi of x plus a equal to c into psi of x. That means wave function at x plus a, suppose this is some x. Okay. At this point the wave function at this point is just a c number, a complex number times psi of x. Okay. So, the wave function at this point and this function this point and this point are related by a complex number c. Okay. So, if you displace the wave function n times the lattice parameter, then you will get the same wave function. Okay. And this wave function is just a c raised to n times psi of x. Okay. Because up to this point this is the first argument. Okay. If you displace the position by n times the lattice parameter, you get the same wave function. Okay. Now, psi of x is basically n times c raised to n times psi of x. Okay. Because psi of x must be single valued function. Okay. It should not be different. So, if you displace n times and suppose the value at this point and this point, or this point and this point are the same, then it should be single valued. It should not get a two different values for the same wave function. Okay. So, then this equation must be obeyed, and if this equation obeys, so let us take these two part of the equation and you can cancel psi of x, and c basically the nth root of unity. Okay. Nth root of 1. Okay, which can be written as like this, where s is given by 0, 1 etc. up to n minus 1. Then psi of x can be written as uk of x with some functions into c of n, is the nth root of unity which is given by this expression. Okay. And this solution satisfies the periodic boundary conditions, or boundary condition in the sense psi of x plus a equal to psi of x. Okay. This satisfies the boundary condition provided u of x k has the periodicity of a, provided uk of x equal to uk of x plus a. Okay. So, if this is true, then it satisfies the periodic boundary condition. Okay. So, this gives you the proof of Bloch theorem. Okay. So, when you have a periodic potential, the wave function will be of the form the plane wave multiplied by a function which varies with space, but it is having a special property that it is periodic in space. Okay. Thank you.